The next example that we're going to discuss is related to substrate degradation and microbial kinetics. This is a typical example of environmental models that are highly demanded in industry, and these are used for monitoring degradation of pollutants or transformation of pollutants in lakes, in reservoirs, in rivers, and also in control systems such as reactors. For this, we're going to discuss more in detail microbial kinetics through the Monod equations. These equations were previously discussed in lecture number 5, and this it is at the basis of all the models describing the interactions between a biodegradable substrate and a microbial mass that feeds upon it. The model equations describing the substrate consumption and the biomass growth in a batch, that is a closed vessel, are the following. These are the general equations, and I'm going to explain in detail what is the meaning of these equations and what forms can they take actually. So as I said to you before, this equation is at the basis of many environmental models in connections with water quality, environmental monitoring, etc. So a substrate is it can be any component that are essential for growth of biomass. Biomass is the description of something microorganisms, but it's a group of microorganisms, or it is a group of a species, a microbial species, a group of different microbial species that are lumped together. These carry biological transformations, and these transformations may deplete what is called the substrate. But it can also be a nutrient, for instance. So biomass will depend of one an important compound along with other components, but one of them may be limiting. For instance, in the case of algae, one limiting component is phosphorus. So this equation can take actually the form of a relation with phosphorus instead of any other compound. Okay, so substrate has a negative sign in this case, and it's because it is the one who is being depleted. It can also be a contaminant, or in a wastewater treatment plant, it can be the organic matter that is being degraded, right? It also includes a yield component because it also includes this is in terms of biomass. This is interrelated to the biomass. So therefore, there is a need to have a yield that transforms the terms of biomass to terms of substrate, of units of substrate. I'm going to stress at this point that these equations, which are differential equations, are not the differential equation yet, the one that describes the stock and flow diagram that later on will be discussed. And why am I saying this? Because these equations at this point are in terms of concentration, all right? So when we are discussing the environmental models where we have inflows and outflows in a system, we will have to transform this, as we have discussed and stressed before, to an extensive, to be working in terms of an extensive variable. When we have the development of our stock and flow equation, that is also it has a differential component because it is a a store component, a storage component that increases or decreases, right? But at this point, we can still dealing with the concentrations because we're just talking about the biological transformations. So in terms of biomass, the biomass also has these constant values that are actually measured experimentally, and these can also be used as parameter values for the calibration or for parameter estimation that we will discuss later. But it also contains a term that is related to decay or to the death of the biomass. This one also we have this equation. We have seen this equation before in lecture number 5, where it also includes a term that is related to maintenance. So this is the basic Monod equation that can take different forms. For instance, for biomass, it can also include, if it's dependent, the biomass, if it's highly dependent on the temperature, we will have a modified version of this equation. Or if it's dependent, in the case of algae, if it is dependent, highly dependent on light, right? On solar radiation, we will have an additional parameter that will be the one that drives the growth of the biomass. So some assumptions once these equations are being solved are that the substrate is supposed to be totally biodegradable and therefore it decays to zero. So you know that this is not always the case, and there might be some remain of the substrate depending on the efficiency, right, of degradation efficiency. That is not actually included at this point on the equation. So the substrate is being consumed by the biomass. Its rate of consumption follows the same dynamics of the biomass growth and the proportion yield factor. Y denotes the fact that for each unit of consumed substrate, Y units of biomass are being produced. There is a fixed fraction of the biomass that decays, and the biomass growth rate cannot exceed its maximum value of growth, which is mu max, the maximum growth rate. The relative speed of the reaction is presented by the so-called half saturation constant, which is called Ks, where a small value implies that the biomass grows at a high rate, near its mu max, even with a limited substrate availability. So all these variables were already discussed in lecture number 5. But what I want to stress in this moment is the fact that these variables depend on the biomass characteristics or the type of biomass. So different type of microorganisms will have different mu max and different Kas. And so we can have these values from literature, but sometimes, well, for instance, in this case, we have a specification of one value, but sometimes we don't have, there are no reports of the mu max of the specific group of microorganisms that we are trying to use for our models. And that is where we may need to start estimating the values of these parameters. So this is not yet a model, an environmental model, but it's more just the plot of the description of these equations in terms of concentration that can lead us to the description of the increase in the biomass as a function of the decrease of the depletion of the substrate. All right? Okay, but in environmental modeling, we're going to have, we as modelers, we are describing a process that includes the biological processes, but it's not the whole story. our focus is to describe how this process is included in the system. So, for instance, we can have we can think about the lake at UQ, and we can think about the inflows and outflows affecting the system. So think about what would be an inflow affecting the system. It can be, for instance, let's think about a rainfall or transfer of a component. It can be an outflow, and we're talking now at this point about the hydrological characteristics. But these things are combined, and not along with the biological process. So an outflow of this system can be evaporation. And how this will affect the biological processes? Well, it will affect the volume in the lake. And if the volume of the lake is affected, then therefore the concentration will be affected. And therefore, we have to think about this process in terms of a stock flow equation that is based on extensive variables. We can also have inflows that contains the substrate that is being used for the biological process. So that means that our system cannot be solely described based on these equations, because this equation is only the small story of the overall mass balance. We can also have outflows of the biomass that is being produced, that will also have biomass that is being produced, for instance, the algae, or we can also have the substrate that it's being used in the biological processes is leaving also the system. So then it means that our overall equations will include, for instance, in terms of mass balances, will include the mass entering the system and the mass leaving the system, plus or minus the consumption and the generation of that specific mass that we're tracking. Let's think about, for instance, nitrogen. So nitrogen can enter the system through the through the inflow that contains this component, and then it can be consumed by some microorganisms, and it can be can leave our system, right? If I'm talking about the nitrogen, we can only have mass in and out. So let's think about better think about one component, which can be nitrate or can be ammonium, for instance. So those things can also be consumed or generated, because those ones are being subject to transformations, right? If we're talking about substrate balances, it will contain the substrate that is entering the substrate that is leaving the system, and minus the substrate that is being consumed. If we're talking about the interaction between one type of microorganism that consumes this substrate. But let's think about other type of biological processes that may actually generate that substrate. That can also occur or can release that substrate. For instance, if we have sedimentation, some nutrients may be released also with time. So then we have other process going on. This term of consumption is the one that the equation that we just saw in the monokinetics, right? Then we also have the biomass balances, and we can have biomass that is entering the system, and we can have biomass that is leaving the system, plus the reaction. And then As you see here, our reaction equation was based in terms of concentration, but we cannot use it in our stock and flow equation, and therefore we have included the volume, the multiplication of the volume, so we can have everything in terms of an extensive variable. Then we may or may not have volume balances. This will depend on whether the volume is being maintained constant, which will mean that it is at steady state conditions, or if we have variation on the volume. If there is variation on the volume, then we will have an additional equation that will also control the other equations where volume is being included. Later on, if we want to know the concentration, we can, of the substrate, for instance, we can have an algebraic variable for estimating the substrate concentration.